Hello everyone, today let's take a look at QP114, a slightly harder inclusion-exclusion problem. So basically we have a 3x3 grid, looks something like this, and each individual square in it is either colored black or white with equal probability. So what's the probability that this grid does not contain a 2x2 subgrid colored entirely white? So I know it's a little bit hard to see the black squares with the dark background, but this might be a random coloring here where these squares are black and the others are white. You can see that in this example, we do have a 2x2 subgrid colored entirely white. It's this one up here, which I enclosed in blue. This is another random coloring where we again have a 2x2 subgrid with all white squares, but it's going to be the bottom left one in this case. So we just need to count the number of cases where this does not happen, and you can see that in our 3x3 grid, we're going to have 4 different possible 2x2 subgrids, right? We could have this bottom left one, we could have this top left, or we could have this top right, or we could have the bottom right, correct? And again, we could do it case by case, but it's going to be a lot easier and faster to do inclusion-exclusion, where we just calculate the total number of ways to tile this 3x3 grid, and then we just subtract off all the cases where this 2x2 subgrid of all white does occur. So first, the total number of ways to tile this grid. Well, we have 2 options for each of our squares, right? It could either be black or white, so we have 9 total squares. So there's going to be 2 to the power of 9 total ways to color this grid. So now let's just calculate the number of ways that we do have a 2x2 subgrid and then subtract that from our total, and that will give us our final answer. So we have 4 different subgrids that could be all white, and I've denoted them by A1 through A4, where A1 is the top left, A2 is the top right, A3 is the bottom left, and A4 is the bottom right. And we want to find the number of events such that any of these are true, so we're basically just finding the union between all of these sets right here, and that's what we're going to subtract from our total. And this is a good question because calculating the magnitude of this union is not going to be as simple as some of the other inclusion-exclusion cases. We're really going to have to think about this. Okay, so to solve this, let's just first start by looking at the magnitude of just A1 by itself. So we have this subgrid up here colored entirely white. So once we've fixed these 4 as white, well then we have 2 different options for the remainder of our squares each, and we have 5 different squares, so it's going to be 2 to the power of 5 different ways to color it when we restrict the top left subgrid to having all white. So the magnitude of A1 is just going to be equal to 2 to the power of 5, also known as 32. And now let's look at A2. And again, the magnitude of A2 is going to be the same as it was for A1 because we have 5 remaining squares and they're all going to have 2 different options, right? So 2 to the power of 5 again, so 32. And you can pretty clearly see that the magnitude of A3 and A4 are also going to be equal to 32 as well. So we calculated the magnitude of our single sets, but now we're going to be overcounting a lot of cases. For instance, this one right here, where both A1 and A2 are true because both of the top left and the top right subgrid will be all white in this case. That's just because when we were calculating the magnitude of A2, so this subgrid up here being all white, we were including the cases where these 2 squares over here were also white. So we counted this specific case right here 8 different times because we have 2 options for our remaining 3, so 2 cubed. But this exact same configuration was also counted when we were looking at the magnitude of A1, so this subgrid up here being all white, because if these 2 squares over here were white, well then we'd have 2, 4, 8 different options for the remaining squares. So again, this configuration is being counted 8 times in this number and 8 times in this number right here. So we need to subtract it 1 time. That's going to be the magnitude of intersection between A1 and A2 when both the top left and the top right are all white. And we already calculated that is going to be 2 cubed, which is 8. And similarly, we're also overcounting the magnitude of intersection between A1 and A3 when both of these grids are colored white for the exact same reasons. We're going to have 2 different options for our remaining 3. The magnitude of intersection between A1 and A3 is also going to be 2 cubed, so 8 as well. And the exact same story for the exact same reasons is going to be true for the magnitude of intersection between A3 and A4, which would look something like this. Again, we have 2 different options for our 3 remaining squares, so it's going to be 8 as well. And the same is going to be true for this one up here, which would be A2 intersection A4. So I've just simplified to make some more space here. You can see that the 4 different single intersections all had value 32, and the 4 different double intersections that we've talked about all had a value of 8, but there's 2 more that we need to talk about. And those are the cases when we have diagonal subgrids both being colored all white. So for instance, maybe this right here, where we have A1 intersection A4. Now this intersection right here was not counted 8 different times. It was only counted 4 different times because we only have 2 different options for our remaining squares. So this arrangement right here was accounted for 4 different times when we were calculating the magnitude of A4 and 4 different times when we were calculating the magnitude of A1. So we need to subtract this off 1 time as well. So that's the interesting part about this question, is that not all double intersections have the same value. For instance, A1 intersection A4 would have a value of 4. And the same would be true for the magnitude of intersection between A2 and A3. We have two different remaining options for our boxes, so the magnitude between A2 and A3 will also be equal to 4. Okay, but now when we take all these 32s and we sum them up and then we subtract off our double intersections, well, now we've undercounted our triple intersections. And why is that? Well, for instance, this specific configuration right here would have been counted 3 different times when we were doing our single intersections, right? So once for this right here, once for this subgrid, and once for this subgrid. But then for this configuration, we also subtracted off the 3 different double intersections that we have here. So this one here, and then we'd also have this one right here. So we've added this case 3 different times in our single intersections, and then we subtracted it 3 different times in our double intersections. So we still need to add it back on one more time for our triple intersection. And the magnitude of this triple intersection right here is just going to be 2 because we only have 2 choices for our remaining blocks. So we're going to have 2, and it's going to be the same story for any of our other triple intersections. You can see there's not going to be any different cases like there were for our doubles. So all my triple intersections are going to have a value of 2. That's just why I put the I, J, and K right there. So now all that's left to find is the magnitude of our quadruple intersection, which would be when every single square is colored white. So there's only one way that this can happen, and it would have been counted 4 different times in our single intersections. It would have been subtracted 6 times in our doubles, and it would have been added back on 4 different times for our triples. So that means that we've counted it a net of 2 times, right? So we need to subtract it 1 time. And the magnitude of it is going to be 1. So now we have everything that we need to solve for our magnitude of union. So we had 4 single intersection terms, each having value 32. So we take 4 times 32, then we subtract off all of our double intersections. 4 of our double intersections had a value of 8. So we subtract off 4 times 8, and then the other 2 had a value of 4. So let's subtract off 4 times 2. Now we add back on the 4 different triple intersections that we had, each having value 2. So 4 times 2 added back on there. And then we just need to subtract off our quadruple intersection 1 time, and it had a value of 1. So we subtract 1 at the end. So these terms right here are going to cancel with each other. This term right here, 4 times 32, is going to be 128. And then we have 32 right here, and we're going to have a subtraction of 1 here. So now 128 minus 33, that's going to be equal to 95. So there's going to be 95 cases where at least one of our subgrids is all white. And we want the number of cases where none of them are white. So we're just going to take our total, which we already calculated was 2 to the power of 9, also known as 512. And then we just need to subtract off the cases where at least one is white, which we just calculated is 95. That's going to give us 417 cases where none of these subgrids are all white. And it's also asking us what is the probability of this happening. So it's just going to be 417 out of our total cases, which were 512. So that will be our final answer.